Hello everyone, welcome to Physmatica. Let's take a look at the solutions for the first week. I'm going to briefly go through all the solutions. I hope you like it, and please don't forget to subscribe and like. So the first problem is that solve this inequality. It's a very simple one actually. It's just the only point about it is that regarding the absolute values. So first let's find the domain of this function. So the domain is simply all the real values. And from here, for the first case, we are going to say that what is going to happen to our inequality if x is always going to be positive or x is greater than or equal to 0. So, simply said, we can just remove the absolute value of the x because our x is always positive. So we were going to get this new form of the equation. And from here, we can simply solve it. We know that we can just replace 1 with 1 plus x over 1 plus x, and from here we're going to get absolute value of 1 over 1 plus x is going to be greater than or equal to 1 over 2. And from here we know that x is always positive, so we can just simply get rid of the absolute values because that function is always positive. So 1 over 1 plus x greater than or equal to 1 over 2, and from here simply said x is going to be between 0 and 1. So now let's take a look at the second case, which is that x is less than or equal to 0. So our absolute value is going to be minus x, so we replace absolute value of x with minus x, and from here, to satisfy that this equation, we know that 1 over x is going to be positive, and we had that x is going to be less than 0 as well, and that's the solution we get. So absolute value of 1 over 1 minus x is going to be greater than or equal to 1 over 2, and from here we can simply say that x is going to be between minus 1 and 0, minus 1 included. So simply said, the union between the two solutions is going to be x between minus 1 and 1, both included. So it's a very easy question. It's from a JEE advanced exam, I believe. Not that difficult, you just need to know a few points regarding the absolute values. Now let's take a look at the second problem. And the second problem is that find the range. This is from a Chinese math Olympiad. It's not that difficult. You just have to know a bit of knowledge regarding logarithms. So let's just solve it. First point is that when we have the bases of the logarithms, there are few rules regarding them. One of them is that base cannot be 1. It has to be positive. And from there, we can also have that 2x2 plus x minus 1 also have to be positive. So from just by solving that, we see that x is going to be greater than 1 over 2. So simply said, that's actually our starting range. So let's solve this. For the starter, take a look at the right hand side. Take a look at a logarithm of 2 with base x minus 1. We can simply say that minus 1 is actually logarithm x with base x, and we know that when two logarithms have the same bases and there is a substitution between them, I can just change the substitution to division, and this is vice versa as well. So I will change logarithm of 2 with base x minus logarithm of x with base x is going to be equal to logarithm of 2 over x with base x. So if I rewrite my equation, this is my new form, and this is what I'm going to solve now. So I'm going to solve this equation and find the range for this equation. So from here, there is 2 points that you need to know regarding logarithms. So take a look at the base x. So because x is not defined, we have to consider two cases. One is that x is greater than 1, and one is that x is between 0 and 1. So when x is greater than 1, our logarithm function is always increasing. And what does that mean is that when we have that, for example, logarithm a with base x greater than logarithm b with base x, because the bases are the same, we can just simply say that a is greater than b. So simply said, if we just extend this law to what we have, we're going to get 2x2 plus x minus 1 is going to be greater than 2 over x. Let's solve this. We're going to get to a cubic function. So we're going to get to 2x2 plus x2, 2x3 plus x2 minus x minus 2 greater than 0. So To solve this cubic equation, if you couldn't quickly get to the root, just remember to always just try to substitute plus or minus 1, plus or minus 2, and plus or minus 3. And most of the time, one of these is going to be your solution. So in here, we can simply see that 1 is actually one of the roots. So we can just factor that one out. So we have x minus 1 multiplied by 2x2 plus 3x plus 2. So we had that it's going to be positive from previous form. So this is simply solved now because we know that 2x2 plus 3x plus 2 is always positive. So the only way this equation can be satisfied is that x is going to be greater than 1. So this is the solution for the first case. Now let's take a look at the second case. Second case is that what happens if our base is between 0 and 1? When we have a logarithm with that base, it's always going to be a decreasing function. So we just have to simply change the sign to less than 2 over x. So let's solve it for this. And this is simply solved. We know that x is going to be less than 1 for that equation to be satisfied because 2x2 plus 3x plus 2 is always positive. And we already knew that x is greater than 1 over 2 as well. We solved this in the start of the problem because we said that x is going to be positive. X can't be 1, and the 2x2 plus x minus 1 is going to be greater than 0, and the solution for that is that x is going to be greater than 1 over 2. So this is actually going to be a union between these, as x is going to be between 1 and 1 over 2. So simply said, the solution between case 1 and case 2 is going to be x is greater than 1 over 2 and x cannot be 1. So practically x is going to be from 1 over 2 not included to positive infinity without the number 1 itself. Now let's take a look at the last question. Is it possible to find 2014 distinct positive integers whose sum is divisible by each of them? So this might not be very clear how to solve this. You need to think about it a bit. So let's just take a look at this example, 1, 2, and 3, this set of numbers. The idea is that if I add all the elements, which is going to be 6, is 6 divisible by each element in that set, which is 6 is divisible by 3, by 2, and by 1. So idea is that can you find 2014 distinct positive integers like that? I'm going to hypothesize something here, and I'm going to say that if I have a set of positive integers whose sum is divisible by each element of the set, then adding a new element equal to that sum produces a new set that also has this property. And you can try to prove this, and this hypothesis is actually correct. So from here we can just say that, let's take a look at this. We have 6, which is divisible. Now we're going to have 12, which is 12 still is divisible by each element in that set, then 24, then 48, and 96, and we can just continue this. So we can simply say that yes, it is possible to write this. For example, from here we have 2008 more elements to get to 2014. So simply said, it is doable. And this is not really a proof, but that's just one example that it's actually possible. There is definitely another way you can solve this. Let me know if you find new solutions, especially for this one. I hope you liked it. I try to be fast and brief, but if you want, I can be more in-depth and actually make separate videos for each solutions and discuss the solutions in more detail. Thank you for watching.